right, hello everyone, and thank you for the nice introduction, and thank you for allowing me to talk about my research today. So as Justin said, I will talk about mantle plumes and specifically what we can learn about them from connecting geodynamic models and seismic observations. And this is work I did together with Renee Gassmöller, Martina Monaco, Bob Myhill, and Sana Kotar. And so first, let me say a bit about why I'm interested in mantle plumes. So plumes are these hot thermal anomalies that rise through the Earth's mantle, and when the plume head approaches the Earth's surface, it causes massive melting and huge volcanic eruptions, and that leads to the emplacement of a large igneous province, such as shown here on the left, the Columbia River basalts. And then later on, the stable plume tail remains in the mantle to cause hotspot volcanism at ocean islands, such as, for example, Hawaii. But what is more, plumes have also been suggested to be connected to environmental catastrophes and mass extinction events. So at the bottom here, we see in this blue curve, the extinction rate of species plotted throughout the Earth's history. And then as these vertical red bars, we see the emplacement times of large igneous provinces, so the arrival times of plumes at the Earth's surface. And we can see that many of those coincide with spikes in the extinction rate. And so why do I want to study these plumes using geodynamic models? As many other features on the Earth's surface, we can only understand the observations that we have about plumes if we connect them to the processes in the Earth's interior. But the problem with that is that the Earth's interior is mostly inaccessible. And this diagram illustrates how inaccessible the Earth's interior is. So most of the data that we have about the Earth is where this green dot is, which is at the present day and at the surface of the Earth. We can go along this horizontal axis back in time because the rock record tells us how the Earth's surface has looked like in the past. We can also go along the vertical axis because geophysical data tell us how the Earth's interior looks like today. But that still leaves this huge part of the diagram where we have very little information available, and geodynamic modeling can help us to connect these data points that we do have and to help us understand how the Earth's interior has looked like in the past. And before I go into applying geodynamic modeling to mantle plumes, I want to give a bit of an overview about the concept of geodynamic modeling itself and what we can learn from a geodynamic model. And so first, what we can learn about the model depends on what kind of model we're looking at. And there are two modeling philosophies I want to talk about, where the first one is the specific modeling. So the goal of a specific model is to answer the question, what causes the specific state of a system based on a specific observation? So one example could be if we have a subduction zone in a specific region of the Earth, what causes the specific convergence rate of that subduction zone? So we might run a number of models with different properties of the Earth's interior and see under which conditions do we reproduce that convergence rate, and that would help us to better understand that specific state of that region. Another approach would be generic modeling, where the idea is we want to answer the question, what causes the general behavior of a system based on a general observation? So if we stay at the example of the subduction zone, we might want to know, why do some subduction zones show trench advance and others show trench retreat? And again, we might want to run a different number of models, some showing each of these different behaviors, and figure out, well, what processes actually cause us to see one or the other in a given subduction zone. So we would then better understand the general behavior of that system. So based on the question that we want to answer, we would pick one of these modeling strategies, and then the general workflow of a modeling study could look like this. So if we know what question we want to answer, or what hypothesis we want to test, the first step would then be to select a physical model. So that means we select what are the equations that we want to solve and what physical processes do we want to include. Or for example, what should be the material properties be in the model? So one could think, well, if we want to model just convection in the mantle, then we probably need a viscous rheology, whereas if we model the crust, then elastic or brittle deformation might be more important. And depending on the model, it might also be fine to just model the solid deformation of the mantle, or we might want to include the migration of melt as well. So once we've picked that physical model, the next step would then be to discretize it, so to translate it into a numerical model. And for that, we would either need to write or need to use some sort of modeling code. And part of that step would also be code verification. So we would need to check that we're actually solving the equations correctly. After we've made sure that's the case, then we would pick a model setup. So we would choose what kind of modeling geometry, what kind of boundary conditions should our model have, based on what modeling strategy we have picked. And then we would go ahead and test that model setup. So we would validate that model setup in a number of test runs to make sure that we're actually also solving the right equations, so that the behavior that's predicted by the model is consistent with what we think the Earth should behave. And so once we've made sure that works, the next step would be to run the production runs and to analyze them. And that would hopefully help us to answer the question we were asking at the start and to either support or disprove the hypothesis. And then we can communicate the model results and hopefully make some scientific progress. And I want to talk about one of these steps in a little bit more detail, and that's the model setup, and specifically how complicated the model setup should be. So there's the saying about modeling that all models are wrong, but some are useful. And that's because the definition of a model is that it is a simplified representation of a more complex natural phenomenon. So all models of the Earth are simplified in some way, and the question is, how much simplification is the right amount? And so here in the top right, I've shown some different properties that could be either simplified or more complex in a model. So, for example, what physical processes are included, what equations we're solving, what the geometry is, if it's 3D, 2D, or 1D, or what the boundary conditions are. And I want to illustrate the issue of the complexity at the example of a human heart, as shown here in the bottom left. So if we wanted to model a human heart, well, we could say we want to make a very complex model that includes all of the different parts of the heart. And maybe that's useful if we want to actually model where all of the blood is flowing and want to know more about how that works. But if we only want the heart as a representation or as a symbol, then maybe it's fine, or maybe it's even better to just have something like the outline of the heart. And then at the very first glance, one would see, oh, that's a heart. But if we make it even simpler than that, so if we represent the heart just as a triangle, then no one will know that what we are looking at is actually a heart. So then that would be a model that's too simple. And it's the same with geodynamic models, where for some applications we might want to have a very complex model, and sometimes we might want to have a simpler model. But then there are some models that might be so simple that they will not be able to tell us something about how the Earth works. But in general, it's not always the case that a more complex model is also the better model, because simpler models are easier to understand, clearer to communicate, and we have to make fewer assumptions. And so I talked about these concepts because I thought in general, even as a non-geodynamicist, it's useful to understand what geodynamic modelers do and how these models are set up to better interpret the studies. And so if you want to know more details, you could go and look at our 101 geodynamic modeling paper in Solid Earth. Or if you happen to go to EGU in Vienna, there's also a 101 geodynamic modeling workshop. And so as a next step, I want to apply this geodynamic modeling to mantle plumes. And specifically, I first want to look at the commented boundary where plumes are being created. Then I want to look at how plumes rise towards the Earth's surface. And I want to look at the upper mantle to see what seismic observations can tell us about the composition of plumes. And so for that, I want to combine geodynamic models with seismic observations. So let's start with the lowermost mantle. So what we see here on the left is the seismic velocity, specifically the S-wave velocity, just above the commented boundary. And specifically what we see here as these large red regions are two regions of reduced S-wave velocity, the so-called LLSVPs, one below the Pacific and one below Africa. But in addition to that, there's also smaller scale heterogeneity. So we see all of these small red patches just above the commented boundary. And those are regions where the S-wave velocity is reduced even more by up to 30%. And those are the so-called ultra-low velocity zones, or in short, ULVZs. And as you can see, many of them seem to be located at the edges of these LLSVPs or at the base of plume conduits. And they also have a large aspect ratio. So they are hundreds to 1,000 kilometers wide, but only 10 to 30 kilometers thick. And it's not really clear what these ULVZs are, so what actually causes the strong velocity reduction. And one idea is that it could be caused by partial melting. So what we wanted to test was the hypothesis that ULVZs contain partial melt constrained to a thin layer just above the cometal boundary. And so if we want to model partial melt, then the first thing we have to think about, well, how would this melt move? And for that, it's important to know that under these lower mantle pressures, the melt would likely have a larger density than the solid. And so we would expect the melt to sink downwards towards the cometal boundary. But then if partial melting is occurring at the base of plumes, the upwards flow of the plume could also entrain or drag this melt along, causing an upward motion. And so the question is, can these combined processes cause partial melt to stay stable in these thin layers that we see in the seismic observations? And specifically, can our models reproduce the observations in terms of the aspect ratio of the ULVZs, the reduction in S-wave velocity, and also the ULVZs are thought to have sharp tops and sides. And so in order to test this, we made a geodynamic model. And this is a model of just the lowermost mantle. So it extends 200 kilometers above the cometal boundary, and it's 600 kilometers wide. And we prescribed the temperature at the cometal boundary at the base of the model. And that's what's allowing this plume that we see as these background colors to move upwards. So the red colors are high temperatures and the blue colors are cold temperatures. And then the top boundary of the model is open, so the plume can flow out at the top. And so because of that, at the sides, material flows into the model, and there the temperature is prescribed to the mantle adiabat. And so then we look at where partial melt is being generated in this model. So that's what we see in these contours here. That's the melt fraction. And so first we let this model run for 150 million years without allowing the melt to move. And then afterwards, the melt is allowed to migrate relative to the solid, and we will look at sort of what morphologies does the melt layer form. And specifically in all of the future slides, I will only show this part of the model so that we can focus in on what the melt is doing. So let's look at one of these models that we ran and just at this small part of the model. As the background color here, we see the porosity, so the fraction of melt being present, and the contours show the temperature. And as I said, first melt is not being allowed to move. And then at this point in time where we see the yellow colors occurring, that's where melt is starting to move. And as soon as melt can move, it sinks downwards into this really melt-rich layer. So let me stop this here. So this is the part where we still are in the steady state of the plume and melt cannot move. And then a little bit later, so here we see as soon as the melt is allowed to move, it sinks downward. And it forms this yellow layer that grows and grows over time, where 100% melt is concentrated. And so if we think about what our model says and what we know about the Earth, the model is not really consistent with the observations. So first, the model shows this growing sort of magma ocean at the cometal boundary, which we know we shouldn't have in the Earth today. And in addition, if there is a layer of 100% melt, that would not be easily detectable with S-waves because it would just look like the outer core to an S-wave. Whereas we know that we see the ULVZs in the observations of S-waves. So we can't have 100% melt. And so we thought, well, if that model does not reproduce the observation, what's the parameter that influences the behavior of the model most? And that would be the density of the melt relative to the solid. And we ran a number of different models to see how the model behavior changes independent of that parameter. So that's what we see here. Each of these panels shows a different model, where the white label indicates the density difference between the melt and the solid. And we already saw in this panel in the top left where the melt is densest, there we see this growing melt layer at the base of the mantle that's not consistent with the observations. If the melt is still denser than the solid, but not quite as dense, we maybe not get this growing melt layer anymore, but we still get melt to be concentrated in this small triangular region at the base of the plume conduit. Then the other model behavior is if melt and solid have the same density. So if the melt does not move with respect to the solid, then we get a more diffuse region of partial melt. And on the other hand, if the melt is less dense than the solid, so in the column on the right, then the melt can move upwards and we get these melt bands in the plume conduit. So we can also have a look at the animation of how these melt bands form. So again, at the start, melt is not allowed to move. And then at this point in time, it starts moving upwards into the plume conduit. And then it moves upwards until it reaches a pressure and temperature that's below the solidus, and then it freezes again. So that's why we only have these melt bands at the very base of the plume conduit. And now we were asking the question, well, can any of these models that we created, can they reproduce the seismic observations of the ULVZs? And so we took these different scenarios and translated our distribution of pressure, temperature, and melt fraction in the model into S-wave velocity. And so that's what we see here in the column on the right. And so if we look at the model where melt is less dense, we can see that we have these two bands again of reduced S-wave velocity. And the amplitude of the S-wave velocity reduction can also reach these 30% that the observations indicate. And what's also interesting is that if we look at the tops in this model, the top of the ULVZ would be quite sharp. Conversely, if we look at the model where melt is not allowed to move, we still get a velocity reduction because of the partial melt. And depending on how much melt we have, we could also reach the 30%. But the gradient in S-wave velocity at the top is smoother, so it's not as steep as in the model above. And then if the melt is less dense, if the melt is denser than the solid, we said all of the melt is concentrated in this small triangle, and it reaches melt fractions that are so high that S-waves can't pass through anymore. So this does not really reproduce at all the seismic observations that we have. But even if we look at the model where melt is less dense, that seems to reproduce some of the observations. This model cannot explain, for example, why we only have a localized occurrence of ULVZs, because we would expect these melt bands to also extend everywhere, and they should be present everywhere above the commented boundary. This also doesn't explain this large aspect ratio of the ULVZs, and it's also thought that they should have a positive density anomaly. So even though these models reproduce some observations, what we saw is that our geodynamic models cannot reproduce the localized occurrence of ULVZs, the large aspect ratio, and the relative positive density. And so because of that, we think that ULVZs cannot result purely from melting the average present-day mantle at the commented boundary. Now, that still leaves the possibility open that we melt some other material at the commented boundary, and that partial melt is present there as a layer. But we have seen that unless the melt is less dense, it would be really hard for the melt to actually stay in this isolated layer of partial melt and not sink down to the core mantle boundary. Now, in the second part, I want to talk about how these plumes rise from the core mantle boundary towards the surface. And that is motivated by a number of observations about mantle plumes. Specifically, we see that when plumes approach the surface before they erupt, there is some surface uplift at the Earth's surface, but in most cases, it's only uplift of a few hundred meters. The other observation is that seismic tomography, such as shown here in the background, tells us that many plumes have a wide plume radius, so of a few hundred kilometers. So, but these observations are very different from what the classical thermal plume model would tell us, which would say, well, the surface uplift should be on the scale of kilometers, and it would predict very thin plume tails. In addition, we also know that the composition of plume-related melts is not compatible with melting of the average mantle. And so in other words, what all of these things tell us is, well, most plumes are not the average mantle. Most plumes have some other composition, so they are thermochemical plumes. And the most likely candidate for this different composition is recycled basalt. So recycled material from the core mantle boundary with a basaltic composition. The problem with this is that this basalt would make the plume denser, and it would reduce the buoyancy of the plume, so that the question is, can the plume still rise towards the surface? And this slide illustrates the buoyancy of that plume. So if we think about a thermochemical plume that would rise from the cometal boundary and then throughout the whole mantle towards the surface, like along that path, sort of throughout the depth of the Earth's mantle, if we know the temperature of the plume and the composition, then we can compute its buoyancy. So some possible temperature profiles are shown here on the right, where yellow is the plume, and the other colors are the different possible temperature profiles for the mantle. And then in the center panel, we see the corresponding buoyancy. And first, let's have a look at this green line, which is a thermal plume. And we can see for this thermal plume, the buoyancy is always positive, so it's always larger than 0. So that means this plume would always be able to rise from the cometal boundary and reach the surface. But it's different for these thermochemical plumes that contain some of this dense basaltic material, illustrated by these other, like the red, blue, and black profiles. For those profiles, we can see there are 2 places where the buoyancy can become smaller than 0. One is directly at the cometal boundary. So this means if the buoyancy there is negative, then the plume would not even start to rise. And the second one is in the upper mantle, so between 300 and 400 kilometers depth. And so let's have a look at what these barriers mean for how plumes can rise through the mantle. So here we see 4 different models of plumes rising through the mantle, where the colors again show temperature, and red is hot and blue is cold. The model on the left is a thermal plume, where we said, well, this one can always rise from the cometal boundary to the surface, and it has this classical shape with the plume head and the thin plume tail. And this would also cause the kilometer scale surface uplift. Now, the other 3 models are different models of thermochemical plumes, where the buoyancy increases from left towards the right. So the plume with the lowest buoyancy, what happens is, so this plume rises, but then it gets stuck here at this upper mantle buoyancy barrier, and we can see that this plume never reaches the surface and would never cause any volcanism. Then if the buoyancy is slightly higher, so even if the temperature is a little bit larger, or if we have less basalt, then we would get a plume that still ponds in around 300 kilometers depth, and then spawns these secondary plumes that reach the base of the lithosphere. And only if the buoyancy is even larger, we would get a plume that directly rises from the cometal boundary towards the surface, and that would be one that also causes massive volcanism and a large igneous province, and could explain these surface observations. And this plume would also cause a lower surface uplift than the purely thermal plume. And we see that this plume also has a wider plume tail than what the classical thermal plume model would predict. So on the one hand, these thermochemical plumes fit many of the observations that we have better. But on the other hand, these thermochemical plume models can also tell us how much basalt a plume can still carry towards the surface, and while still being able to reach the surface. And that's what's shown on this slide. So each of the dots shown here in one of these diagrams is one of the models that we ran. And so we ran lots of different models. And what the 2 panels show is, on the one hand, the left panel shows the excess temperature of the plume when it approaches the surface versus its initial temperature. And the panel on the right shows the fraction of basalt in the plume also versus its initial temperature. And then the green bars in the background, they show what we think based on observations, what these properties should be. And then the filling of the symbols tells us what type of plume it is. So the solid symbols are plumes that directly rise from the cometal boundary to the surface. The half-filled symbols are the secondary plumes, and the empty symbols are the plumes that pond and never reach the surface. And so what we can see is, if we look at the plumes that fit the excess temperature at the surface best, so we know the excess temperature of the plume should maybe be not more than 250 or definitely not more than 300 Kelvin. So the best ones would probably be the plumes in those areas. If we think about, if we go to the other diagram and look at how much basalt they can carry towards the surface, we can see it's around 15%, maybe a little bit more, maybe a little bit less. But that's how much they can carry. And so if we increase the plume temperature more, that would increase the buoyancy, and so then they would likely be able to carry more basalt. But then the temperatures would fall out of the range of what we think is realistic for the Earth. On the other hand, if we make the excess temperature colder, then what happens is that we get to these secondary plumes that cannot directly reach the surface anymore. So in other words, these plumes with 15 to 20% basalt are directly at the limit of being neutrally buoyant, so they can just reach the surface. So that means if we would make them any heavier by putting more basalt in, they would get stuck and would not be able to reach the surface anymore unless we made them hotter, but then they would be too hot to have a realistic temperature. So in other words, these models tell us that plumes can carry no more than 15 to 20% of this dense recycled basaltic material towards the surface if we want them to have a realistic temperature. So this is the story from geodynamic modeling, but then seismic observations tell us a different story about plume compositions. And specifically, the observation that I'm talking about here is the X discontinuity that is observed beneath Hawaii and also some other hotspots. And here in the bottom left, we see a receiver function study from Kemp et al. And specifically, it's a profile beneath Big Island. And we see in the western part of this profile that the study finds the 410 discontinuity and the 660 discontinuity. But if we go towards the eastern part of the profile, we see that the 410 discontinuity vanishes. And instead, we see the X discontinuity here in 300 kilometers depth. And the interpretation is that this X discontinuity is caused by the coesite-stishovite transition in basalt that occurs around that depth. And so in order for that to work, what would have to happen is that we have a plume that contains some basalt, and this basalt might accumulate in this depth range of 300 to 400 kilometers, and then it would cause our observation of the X discontinuity. Now, the problem with that is that we would need 40% of basalt to reproduce these observations, but we just saw that plumes can only carry 15 to 20% basalt, otherwise they wouldn't be able to reach the surface anymore. And so we wanted to set up geodynamic models to see if there's another mechanism so if we have a plume that only carries 15 to 20% basalt, if there's a mechanism that would allow basalt to accumulate up to this percentage to reproduce the observation of the X discontinuity and to resolve this contradiction between these two studies. And well, for that, we set up geodynamic models. And if I say we, I mostly mean my PhD student, Martina Monaco, because she's the one who set up and ran these simulations. And specifically, the models we looked at are models of the plume conduit just in the upper mantle and in 2D, and they are 600 kilometers high and 400 kilometers wide. And what we did is that we prescribed the upwards flow of the plume on the left and the top boundary of the model, and then had an open boundary that allowed material to flow in from the bottom. And what's special about these models is that we wanted to look at how these basaltic heterogeneities could move relative to the rest of the plume. So what we see here as these red blobs, those are the heterogeneities of basalt moving into the plume. And we wanted to see, well, under which conditions can these heterogeneities accumulate in this depth range of the X discontinuity. And the two properties of the model that are most important for how the heterogeneities move are, on the one hand, the density, and on the other hand, the viscosity. So let's look at those two properties. First, let's have a look at the density. So this diagram shows the simplified density profile for pyrrolite, so for the average mantle, what would be in the plume, and for basalt in the upper mantle and the transition zone. And so what we can see, what we already saw in the previous models, in this depth range between 300 kilometers and 410 kilometers depth, that's the region where basalt has the highest density contrast compared to pyrrolite. And that's because at 300 kilometers, we have the coesite-stishovite transition, where we increase the basalt density. And then at 410 kilometers depth, we have the olivine-wachsleite transition, where the density of pyrrolite increases. And so that means between these two transitions, the density difference between basalt and pyrrolite is around twice as much as the density difference below. And that can provide a mechanism for these basaltic heterogeneities to accumulate in that region, because, well, if they are denser up here, they might sink down. And if they are not quite, if the density contrast is smaller down here, they are more likely to be carried up. And so then they might accumulate in this part of the mantle. The other property I mentioned is the viscosity of the model. And so here we see 3 different models and how they evolve over time. And each of the model has a different viscosity, with the viscosity increasing from the left to the right. And the background color shows us the density in the model. So the bright yellow blobs, those are the basaltic heterogeneities. And then these, the 2 depth ranges that we see here. So this is the 410 discontinuity, and this is the depth of 300 kilometers. And so what we can see in the model with the lowest viscosity, there's very little friction between the basaltic heterogeneities and the plume itself. And so what we see is that all of these heterogeneities, because they are dense, they sink downwards, and very little basalt is carried through the region of these phase transitions. On the other hand, if we go to the model on the right with the very high viscosity, because the viscosity is so high, there's very little deformation at all inside of the plume. And so the plume basically carries all of these heterogeneities towards the surface, which means we do have more basalt in the region of the phase transitions, but there's not really a mechanism for the basalt to accumulate. And only in this model here in the center with the intermediate viscosities, we can see that basalt is carried towards the surface, but the heterogeneities can also move relative to each other because there's internal deformation in the plume conduit. And so we can see in this case, the basaltic heterogeneities often sink in this region beneath the 300 kilometers depth. And so we see at some points in time, there seems to be some accumulation of basalt. So if I go all the way to the end of this simulation, we can see that it seems like in this region, there's a lot of basalt present. But of course, we should look at this more quantitatively. And so that's what we see on the next slide. So here, each curve represents the average amount of basalt, like averaged over a layer of 100 kilometers width, so between 260 and 360 kilometers depth. So that's sort of the band just around the coesite-stishovite transition. And it's plotted over time, so throughout the model evolution. And then each different color is a different model, where the purple curve represents the model that we saw on the left, so the one here with the very low viscosity. And we can see that was the one where basalt is not carried towards the surface, and we see that represented as very low basalt fractions, below 10% throughout most of the time. The green curve is the model that was on the right with the very high viscosities. And we can see in that case, the basalt fractions are larger and they oscillate around some average, which is 15%. In this case, it's the amount, like the average amount of basalt within the plume carried in from the bottom. And these oscillations are because we have these separate heterogeneities. And if they, like when one of these heterogeneities reaches the phase transition, we have a higher percentage. And if there are few heterogeneities near the 300 kilometers depth, then we have a lower percentage. But then if we look at the yellow line, that's the line with the intermediate viscosities where we have a mechanism for basalt to accumulate. And we see that it also shows these variations in basalt fraction. And this is the only model that actually reaches percentages of more than 40%. So what we would need to explain the X discontinuity. But we can see that it doesn't have 40% of basalt throughout the whole time, but that only happens at this one specific point in time. And it would have to be a really big coincidence that not just Hawaii, but also several other plumes are at like exactly this small snapshot in time where there happens to be a lot of basalt near 300 kilometers depth. And so we can quantify sort of how much basalt we actually accumulate throughout the whole runtime of the model by averaging our basalt fractions through the whole model runtime. And so that's what's shown here. So each bar represents the basalt fraction not only averaged over a bin of 100 kilometers depth, so at like 210, 310, 410, and so on kilometers depth, but also averaged over time. So basically taking all of these basalt percentages and then averaging the whole time range. And so again, the model on the left is a model where the viscosity is low and all of the heterogeneities are sinking. And again, we see that the basalt fractions overall are also low, below 10%, and that they decrease from the bottom towards the top of the model because less basalt is carried upwards. If we go to the panel on the right, that's the model with the very high viscosity where there's no internal deformation in the plume. And so we can see because of that, all heterogeneities are carried upwards without any deformation. And so if we average over the whole model evolution, then we basically get the same amount of basalt in any depth range, because that's just the average amount of basalt in that plume in the model. But we do get different basalt distributions with depth in the model with the intermediate viscosities. So there we do see some effect of accumulation. And specifically, if we compare the bar at the bottom, which is the amount of basalt flowing into the model, so the average amount of basalt in the plume, we can see that even averaged over time, we have more basalt at around 400 kilometers depth. And we also still have more basalt at around 300 kilometers depth, even though it's not quite as much as at 400. And then we get less basalt again if we go further upwards in the plume conduit. So why is that the case? That's exactly this effect of the high basalt density that we talked about, that the biggest accumulation occurs around 410 kilometers depth, because above that, the basalt is really, really dense and tends to sink downwards. And below that, the density contrast is lowest, so the basalt tends to be carried upwards within the plume. So around 410 is where most of the basalt would tend to accumulate. And while we still have basalt accumulation around 300 kilometers depth, if we look at the absolute numbers, we can see that it's only a small percentage. So compared to the average amount of basalt in the plume, which would be around like 18 or 19%, we can see that even like averaged over time, even the amount of basalt at 410 would only be around 5% more. So that means if we look at the whole plume over time, we can never get from a plume that has 10 or like 15 or 20% basalt to a plume that has 40% basalt. So we cannot sustain this basalt fraction that's needed for the X discontinuity to be observed throughout the whole model time. And so that means while this mechanism explains some basalt accumulation, we need some other or additional mechanisms to explain how we would get to the 40% of basalt within the plume. So to summarize the whole talk, we first looked at the creation of, or like the stability of partial melt near the core mantle boundary. And we saw that this melt can only stay suspended if it's less dense than the solid, or if it's almost neutrally buoyant. And otherwise, the melt would sink down to form a completely molten layer at the core mantle boundary that also grows over time, which would not be consistent with the observations. We also saw that geodynamic models, because of this, they cannot reproduce the localized occurrence of ULVZs, the large aspect ratio, and the relative positive density of the ULVZs. And because of that, we think that ULVZs do not result purely from melting of average present-day mantle material at the core mantle boundary. Then we've looked at how plumes rise through the mantle, and we saw that they can carry up to 15 to 20% of denser recycled basaltic material towards the surface. And we also saw that this basalt can accumulate in plume conduits in a depth of around 250 to 400 kilometers, because that's where the basalt is particularly dense. But while basalt fractions in that depth can reach more than 40% at specific points in time, even if the plume itself only carries 15 to 20% of basalt, we saw that this only happens temporarily at specific points in time, and it cannot be sustained for longer times for a plume conduit. And so if we want to explain the X discontinuity, we need to find some other mechanisms. Thank you.
Thank you very much for that fabulous talk, Juliane. That was really, really interesting modeling results there that you shared. For those folks that are here live, please feel free to enter a question into the chat box if you have any questions. I'm sorry, the Q&A box. You could put them in the Q&A box. That would be great. I do have a few questions to start us off, and I must confess that I'm coming at this from a somewhat ignorant point of view in that I'm not a geodynamicist, but I was curious to know, your last point talking about how the plumes could carry no more than about 15 to 20% of recycled basalt. I wondered in my mind, I'm assuming that this recycled basalt, it's coming from descending slabs, right, that are melting as they descend into the mantle, basaltic slabs. And I'm wondering if that causes the percentage of basalt in the mantle to rise with time, or if it ends up getting evened out because of the eruption of basalt at places like mid-ocean ridges.
So I guess that depends a bit on how you count, like what's the fraction of basalt. So if you take the whole slab from the surface and put it into the mantle, you get the part of the oceanic crust that is basalt, and you also get the part of the lithosphere that is Harzburgite. And so if you think about the whole history of the Earth, depending on when plate tectonics started, you could say, well, probably the whole mantle has been recycled at some point. And so because of that, all of the mantle should either be basalt or it should be Harzburgite. So in that sense, over the history of the Earth, if the initial composition of the Earth's mantle ever was something that's like that you would call pyrrolite, and it was like a chemical mixture with like a pyrrolite lithology, then you would say over the history of the Earth, you would change the mantle so that it has more basalt and Harzburgite and it's less of the initial composition left. But I think like today, you would assume that most of the mantle has undergone the melting cycle at least once. And there are only some reservoirs that have some of this primordial material left. Okay,
that makes sense. I had a question about these basaltic heterogeneities that appeared in your model. To me, they look like blobs that are sort of like rising through this plume. And I'm just wondering how realistic that interpretation is. I mean, if those blobs of basalt are really present in nature, would you expect to see evidence of that in the erupted material? Like you'd have, volcanic centers in close proximity, some of which are highly basaltic and others that are less so, things like that. Is that a reasonable interpretation?
Yes, and I think that is actually something that we do see. And so so we don't know what the length scales of these heterogeneities should be, and observations are actually the only thing that could tell us something about the length scale. So I'm not a geochemist, but from what I understand about geochemistry, it's like harder. So because we extract the melt, and then the melt, like it's partial melt, so the melt at the surface would have a different composition than what the plume source would have. It's harder to constrain sort of if the original composition would be basaltic or if it would be pyrolytic or some other composition. But what's done a lot is to look at the isotopes. And so there are a lot of studies of isotopes that tell us, well, if we look at the erupted materials at the surface, is that more recycled, or is that sort of more average mantle, or is it some recycled, like something that we think is recycled basaltic material? And so many of these studies show on a really small length scale that there are these heterogeneities within plumes. And so that there are differences in these isotopic trends on the length scale of tens of kilometers or even a few kilometers. Okay. And that's what we can use to constrain how big these heterogeneities should be.
Oh, interesting. Okay, well, that makes sense. We did have a question here from Cindy Evinger, and she says, great talk. It says, given the larger than 50 million year persistence of these ultra low velocity zones based on surface magnetism, can we further narrow models? What volumes would be needed to maintain Pacific and African plumes, for instance?
So first, thank you. And then maybe I need some more clarification on the, so maybe I didn't quite understand the question. Maybe I can look at it in the...
Well, maybe what I'll say is, Cindy Evinger, if you want to go ahead and unmute, you're welcome to ask your question.
Yeah, I just was thinking that given the interaction with the lithosphere persists for such a long time period in some of these large zones, is there an additional constraint or way to narrow models by just looking at the sheer at volumes required to maintain a plume for such a long time period? Some of these large provinces, and just just trying to not trying to get at the really tough chestnut of the X discontinuities specifically, but wondering about longevity as a constraint.
So in order to look at the sort of like the longevity of plumes, I would do that more in sort of like global 3D models, and when running some of these models, like in those models, plumes are stable on these timescales of like tens of million years or even longer, and they can stay in their location on the one hand because like sometimes sort of the large scale mantle flow patterns stay the same for a long time. So I think so generally the idea that, so the way I imagine the mantle today is, right, we have these two large low shear velocity provinces, one below Africa and one below the Pacific. And between that, we have slabs coming down into the mantle. And so as long as that pattern stays as it is, we would have plumes upwelling around the edges of these LLSVPs. So, and that's what also observations say, that sort of this pattern has stayed stable like this for a large amount of time. And so then we would, so I'm not really sure how I would connect that to the volume of the erupted materials, because the plume, right? The plumes are so big, and there's always like some new material from the thermal boundary layer at the cometal boundary available to entrain that into the plume. And so, is your question more about like what makes the plume stable?
No, it was the volume of material at the core mantle boundary available to maintain sharp-sided plume structure over long time periods. And then just in saying that the steady supply of slabs is enough is what is basically my question. So not the surface volume, it's the volume of material required to maintain that kind of structure and that at the core mantle boundary.
So what we see in those 3D models is that it's not that much important. Like it's not super important what the volume of the slabs in itself is, but it's enough to have downwelling material and sort of downward flow that pushes against the edges of the LLSVPs, and that's already enough to make the edges steep. So you don't need specifically a slab pushing against the side of the LLSVP, but it's enough to have. But as long as there's some downwelling material, and as long as there's continued conduction at the cometal boundary, so that you have a thermal boundary layer where you can source hot plume material from, that's enough to get to continually sort of get upwelling plumes and at the edges of the LLSVPs, and they would keep steep edges.
So we did have a second question come in about these ultra low velocity zones. And just wondering what the typical lifespan of one of those would be. I mean, do they break down at some point, or is the theory that once they're formed, do they sort of exist forever?
Yeah, right. So that's an interesting question, and it would depend on what they're actually made of, right? It would be so like the question that I looked at was, well, are these made of partial melt? And so if they're made of partial melt, then it would depend on the temperature. So as long as it's not hot enough for the material to be molten anymore, they would go away. But sort of one of the conclusions of this was that it's, let's say, unlikely that they're made of partial melt, or at least it can't be partial melt of the present day composition. And so the other idea is that they could be compositional heterogeneities. So that would require a chemical composition that can reduce the seismic velocities by 30%. So it would have to be some really specific composition. And in that case, what has been suggested is that it's a really iron-rich composition that would keep that material down there basically for over the whole history of the Earth, because it would be something like 10% denser than the average mantle, which would mean it would never be entrained upwards within the plume. And so if that's actually the case, then at least that material would be there for the whole time. And then they could be moved around, and their sort of their topography, like how high they are, and where they are located would change on the same timescales of the large-scale mantle flow. So it could change on the scale of like tens or hundreds of millions of years, but at least the material would then stay there for the whole history of the Earth, or like since whenever it has been created.
Okay. We had a question with regards to that accumulation zone. They had up to 40% basalt. And the question asks if the movement of the mantle beneath Hawaii would contribute more to that or or less to that. I guess the way I'm interpreting it is the mantle flow beneath Hawaii, is it additive to that and it would contribute to that development of that 40%, or would it take away from it?
So I think that depends a bit on the sort of on the large scale mantle flow beneath Hawaii. So I guess so the way I understand the question is like sort of if there's a large scale upwelling sort of in the general area of where Hawaii is located, could we then have more than 40% in the plume because it would sort of support that upwards flow? And I think potentially that could be the case, but I think the contribution would be very small because sort of the scale of large scale, like the sort of the speeds of these large scale convective motions in the mantle, like it would be much smaller than the contribution of a plume, right? So if we think about a plume, it would potentially be like for Hawaii 200 Kelvin or more hotter than the mantle, and so that would provide the biggest amount of driving force and of buoyancy force for material to move. So I think the motion of the mantle beneath Hawaii, I'm not sure how much it could contribute to like accumulate more than 40% basalt. What I thought about as like another possibility to have potentially more than the amount of basalt that we see in our models is, well, if the background mantle already is a mixture of basalt and Harzburgite, then we also would have some basalt sort of in the mantle matrix that's in the plume. And that could contribute to having more basalt than what we see in our current models.
Maybe one final question here. This is actually for me. I was curious, are there any critical observations, seismic, temperature, chemistry, that you don't currently have that would significantly improve your modeling efforts? And if there are, is there any prospect of getting these observations in the years ahead?
I guess that's I would have to think about that for a bit.
It's kind of a big question, so yeah, sorry about that.
So I think in the recent years there have been a lot of exciting, like, so the sort of the two types of observations that I've mostly been looking at is like on the one hand, geochemical observations that would tell us what's the composition of the plume, and on the other hand, seismic observations that actually image the plume in the mantle itself. And like throughout the last years or the last decade, there has been a lot of exciting progress that has told us more about plumes and led to all of these studies, like these the geochemical studies of the heterogeneities within the plume itself, and then also the sort of the seismic studies that showed us sort of the shape of plumes from the surface to the commented boundary. And so I think what would be exciting is, so like not all of the hotspots that we see at the surface, not for all of those we see sort of what the shape is of the plume in the mantle. So not all of them we can follow to the commented boundary. But I think what we would really want to know is, right, we talked about the LLSVPs and that they are like regions of, like they are these really large regions in the commented boundary of reduced S-wave velocities, but people still don't know what they are actually made of. So most people say they should be made of, like they should have some different composition than the mantle. There are still some people who say, well, maybe they are just hot and they have the same composition of the mantle, but it's still unclear like what this material actually is that is in the region where the plumes start to rise to the surface. And so like that's something that we really want to know, sort of like what's that material in the source region of the plume. And so there have been lots of seismic studies trying to constrain the relative density of this material. Or also, so there's this idea that there are specific geochemical observations that could tell us what the material is made of. And I think like getting better observations to better understand what that composition is would also be really exciting to better understand mantle plumes.
Okay, great. Well, Juliane, thank you so much for your time today and for sharing your exciting science with us. We really appreciate it. And thanks to all of you for tuning in today as well.
Yeah, thank you. That was great. And thanks everyone for listening.